Hi everyone, Mr. Chu over here. Now I'm going to go through the last part of topic 9, which is on 9.3. And this is one of the more difficult part of 9.3 because there are sub-concepts before we use it together to explain and understand what is meant by thin film interference. And there are a few scenarios that we'll go through to help you understand how thin film can actually cause interference and how it appears dark and bright. So let's go through the first part. Now, if I got a piece of material with a refractive index n, and the light goes through it, say the thickness is d, and the speed of light in the material will be c upon n. That's the refractive index over here, because refractive index is defined as c over v, which is the v of the material, the speed of light inside the material over there. Therefore, the time it takes for the beam of light to cross this material will be d divided by c upon n, which is nd divided by c. Now imagine another beam of light were to pass through this region over here. Do you agree that you travel a longer distance? So the question is how much longer? So let's take a look. Can you see that in the time that this beam of light travels through this material, this beam of light will travel through a distance of speed of light. Now this beam of light over here is traveling through air or through vacuum, so there is no change in the speed of light. It is still c multiplied by the time, which is over here. Therefore it is equals to nd. Now this is an important conclusion, that whenever a beam of light travels through a material and it travels through a distance d, then this beam of light travels through a distance of n times d, which makes sense because n is always bigger than 1. So the distance traveled by the beam of light in air will always be bigger than d. So it's n times d. Now, this is the first part of the equation. Now, the second part of the equation is this. Imagine that if I got a wave that goes this way into a tight end. So the string over here is tied to the wall. Now when the wave reflects off, it is going to reflect off this way. So you reflect the wave the other way around. Why? Because when the string over here tries to pull this point up, it can't because it is tight. And therefore the knot or the hinge over here will exert an equal and opposite force on the string, and hence the string will be pulled down. So the force exerted by the wall on the string is equal and opposite, it's down. So therefore the wave gets reflected. Why this part over here? Because this hits the wall first, so it leaves the wall first. Now what's the implication? So we develop this into this. Now imagine a wave were to come in like this. The outgoing wave will look like this. So we can say that the incoming wave and the outgoing wave, they are shifted by half a wave. So there is a phase shift of pi radians. Now why pi radians? Remember that when we talk about phase difference, it is 2 pi upon lambda times the delta x, which is the amount by which you shift the wave. So as you can see over here and over here, if you shift the wave by half a wavelength, basically from here to here, so from this position to this position, you'll get back the same wave. So the phase difference is pi, and there is effectively a path difference of lambda upon 2. So this constitutes an effective path difference of lambda upon 2. So the reason why we don't talk about path difference over here initially is because there is no literal path difference. There's no like two paths traveled by the same wave, so, in this case. But if you look at this situation, it is equivalent. It is not the same, but it is equivalent to a path difference of additional path difference of lambda upon 2. So let's combine these two, this one and this one. The idea that when you have a beam of light traveling through a material, the other beam of light that doesn't travel through the material will travel a distance of n times d when the beam of light in the material travels through d. Second concept, whenever you reflect off a medium that is denser, we can imagine it as being denser. This one, the simulation analogy over here is that it is a tight end, meaning that the wave cannot enter this region easily. So what I'm trying to show over here is that when the light wave tries to enter a region that's difficult to enter, it will reflect off with a path difference, equivalent path difference of lambda upon 2. So that is to say, from a less optically dense medium to a optically dense medium of higher refractive index, there is a path difference of lambda upon 2. But of course, if you switch it around from a more dense region reflecting off a less dense medium, like glass reflecting off air, then there is no path difference of lambda upon 2. Okay, so let's combine these two and let's take a look at this scenario over here. X, light comes in here, light reflects off here and reflects off here. This is beam A, beam B. Now this is air, X, air. So let's understand the scenario from part 1 over there. Now the light over here travels through a distance t, 2t rather. So the path difference, the additional distance this travels through will be 2nt. Right? Because based on this one, whenever the light travels through the medium and travels through a distance d, then you travel through a distance of nd. This one travels through a distance of 2t, this will travel through a distance of 2nt. Now, remember the reflection also contributes. It is reflecting off a less dense from a less dense to more dense. So there is a lambda upon 2, more dense of a less dense, 0. So therefore, the path difference is effectively, I think I combined the 1 and 2 already, is equals to 2nt plus lambda upon 2. Now, back to the basics. If it is equals to constructive interference, if it causes constructive interference, then it should be m lambda. So therefore, 2nt is equals to minus this, and this is constructive. Now look at how you need to be careful over here. I wrote this as m instead of n in case it confuses with the refractive index, because this, if I put n, you may be confused with the refractive index n over there. Now the path difference, if it is equals to m plus half lambda, it is destructive, and therefore 2nt is equals to m lambda for constructive. Now take a careful look for destructive. Take a careful look at this expression. Now, in the past, we learned that 2nt equals to m lambda is constructive and 2nt equals to m minus half lambda is destructive. Look at how the condition is being swapped around. Now, you may notice that the main reason why it is swapped around is because of this. So, I will always recommend whenever you handle thin film interference, write down this part and write down this part and then equate it to m lambda or m plus half lambda depending on whether this is bright or dark, constructive or destructive, and then you construct the necessary equation. Otherwise, you might be confused. Say, for example, in the case where I have a y, x resting on y, and n of x is equals to 1.2, n of y is equals to 1. Probably I write it on the other side in case it is out of screen. So let's use this portion here. Now this situation that we went through just now is air x air. So what if we have a situation of air x y where nx is equals to 1.2, ny equals to 1.4. So reflect off, path difference is equals to, if this is t, 2n of xt plus air of x less dense over more dense, lambda upon 2, x reflecting off y, another lambda upon 2 because it's less dense, more dense. So 2nxt plus lambda. Now for path difference equals to m lambda for constructive, 2nxt is equals to m minus 1 lambda. Now m minus 1, integer minus 1 is still the same, so I'll just put it as m lambda. Alright, if you're more comfortable, fine, we leave it there. But the idea over here is that it is integer number, which is the same as before. So compare this with this. This is constructive, you have m minus half lambda, whereas this is m minus 1 lambda. Integer, integer plus half. So you have to be careful what the base layer is. Now, instead of remembering all the different scenarios, I recommend that you know the basics. That is, the path difference is comprising of this portion and this portion. Yeah? And this is subdivided into two because they're two reflecting medium. All right, so you need to be, in summary, you need to be able to write this portion, the first part of the path difference, and write this. Sometimes it is lambda upon 2 plus 0, sometimes it is lambda upon 2 plus lambda upon 2. Right? Never a case of 0 upon 0, because then it's more dense, off less dense, more dense. In your syllabus, usually it isn't. Okay? So let's try a simple question. Now, if I have a glass coating over here and this is air, now reflects off, reflects off. This is your multi-coating for your glasses. And Nx is equals to 1.3 and this is equals to 1.1. So let's take a look at the minimum coating thickness to cause the wavelength or the light to have minimal reflection. Imagine that the wavelength is 600 nanometers. So let's put it as 1.5. So minimum reflection means constructive or destructive. That's the first thing you need to understand. It is destructive, because if it has minimal reflection, it means that the two beams of light over here must interfere destructively. Now let's use what we learned just now. No matter what, it will always have 2nxt, which is the thickness over here, plus, let's work it out carefully, less dense, more of dense, lambda upon 2, more dense of less dense, so it doesn't matter whether it is air or glass, it is still 0 over here, so long as this is less dense than this. Therefore, if we want destructive interference, 2nt plus half lambda must be equals to m plus half lambda. Therefore, 2nt equals to m lambda. Now, if I want to find minimum coating, what should I set for m? Cannot be 0, it doesn't make sense. Cannot be 2, because that's not the minimum. So therefore, m is equals to 1 and hence lambda 2n over here. So all you need to do is take 600 nanometers divided by 2 times 1.5, which is 200 nanometers. That's the thickness. All right. So if you were to decrease the thickness, one interesting thing is if you decrease the thickness to 0, it will also be close to 0, it will also be dark. Why? Because if I decrease the thickness to close to 0, this will go to 0. And then the path difference will simply be lambda upon 2. So that will cause a destructive interference as well. But of course, it is difficult to get a coating that is of 0 thickness, so it doesn't make sense. Impossible to achieve. Near 0, 1 atom thick, not easy to control. So therefore, we go for this condition where t is not 0, and hence we got 200 nanometers. Okay, so I hope that you have a better understanding of thin film interference. Just do a quick summary. There are two components to the path difference that you need to know how to write. 2nt is one portion, then the other portion is the reflection of the two layers. Remember that whenever you have light traveling from less dense to more dense, add a lambda upon 2. More dense reflecting off a less dense, no need to add lambda upon 2. Then you'll be able to handle all scenarios. Just need to write path difference equals to m lambda, the total path difference equals to m lambda for constructive, m plus half lambda for destructive. And then work out the 2nt equals to this, whether it's constructive or destructive. Okay, I recommend that you don't remember all the different kind of scenario. There's just too many to remember probably. So it's always good that you are firm with your basics. In case they twist the question, you can still handle it. All right, have a good day. Thank you.